Today, I'd love to talk a little bit about nanotechnology in blend agriculture. And you might wonder, what is this? What the heck is this topic? Is this already true? Do we have now nano beside gene tech and whatsoever in agriculture? And I thought it's worth having a look. I would like to talk a little bit about the status, about the risks, and of course, about opportunities we have in this field. Before I like to start, this is, of course, not my work alone. A lot of members from my group and other universities are involved. So at first, I would like to, thanks to my group, thanks to the many people working here at Edge Environmental Geosciences. You know, maybe this nice building here is the UZA or UZA2, and in German Umweltgeowissenschaften. So that are some of the group members. It's not the most recent pictures, but some faces like this one here or this or that you can still remember over there. So thanks a lot to my group, which is a lot of the work doing I will present today. Let's get started. So my introduction will be a little bit about food production on our planet and planetary health. What are the big concerns? And from there, I would like to switch into an introduction in nanotechnology. What is it all about in nanotech? You all heard about this, but I would like to go a little bit into the details and problems, and then I would finally like to go to nano-enabled plant agriculture. In my outline, I had plastics in. Plastics is a big issue in agriculture, but I would love to leave this for the discussion. Why? Because I ended up with 50-something slides and then it's just too long. So I skipped the nanoplastic and plastic part here, but we can discuss this later after the talk. Okay, let's get started. So plant agriculture in the Anthropocene, what is important? You know that our population is increasing. There are several estimates by the UN. I would say the best estimates are roughly around 10 billion in 2050. So you might argue if it is 9.7 or whatsoever. There's even a debate if it will further increase. I would say the best scenarios I know is that this curve is flattening, that we level off about 10 billion, and then global population probably is decreasing. What this means, of course, is that we need more food to provide. Also important is that 80% of people will reside in cities. And you also know that unhealthy and unsustainable produced food is a global risk. Numbers are a little bit diverse at the different perspectives, but let's say roughly you need between 60 or 70% increase in agricultural production. And here in the major countries, nowadays it's China, India, and the US, and this in 2050 will change. So India will be the world leader in population, then China, and then Nigeria. If we look here, what is the increase, for example, in maize, it's about 67%. If you look to corn or wheat or beans, it depends a little bit. And of course, it depends also on the literature you're looking in, but you need a significant increase. And if you look to the estimates, what is the food, what we need, and what is the increase in food production, there's definitely a gap. So there is, by the FAO, by the UN, there is a big fear that there is a gap in food production at our planet. Of course, one of the main drivers here is meat. So if you see the predictions for meat, 64 to 116 million tons mutton, pork, poultry, eggs. So in all these stocks related to meat production, the increase is significant, most in poultry. And meat, which you will see later, is of course one of the big drivers if we consume too much meat, and that's actually what's happening. There are of course other drivers globally. For example, we have 820 million people currently with insufficient food, but 1/3 of all food is wasted. You just can look to the supermarket. Maybe you can even look at home. You can look globally at production chains. Most of the food, by the way, is not wasted at your fridge. It is wasted from the field, on the field, because the cucumber is not perfect, the apple is not perfect, and then it's thrown away at the field. So that's the major source here. 2 billion people are deficient in micronutrients. That's a big issue. So if you think about rice or corn, micronutrients, trace metals are decreasing, and you have health problems from this side. So food production needs to increase depending where you're looking at, which type of food. It's between 60–100%. Food security and food safety is a major challenge on this planet in the next 30 to 40 years to come. Let's look on the pressure on planet Earth. Food production at the same time is the largest pressure on our planet Earth. Let's look first to the climate. Maybe that's an interesting number for you. So agriculture is responsible for 56% of non-CO2 gas emissions, like methane, for example. And it's responsible for roughly 20–30% of the total greenhouse gas emissions. So it's a big player here. So it's the largest non-CO2 greenhouse gas emissions globally, up to 30% of the total greenhouse gases. And then if you look to climate change and projected yield, I just explained in the last slide, we need more food. And then if you look at different modeling scenarios to the climate, like plus or minus, and then you have a check on all these scenarios, you can check the literature here. In average, the decrease due to climate change is more than 10%, which means that impact of climate change on food production is negative. So we are getting into a situation of more climate stress. Climate is getting hotter, rain distribution is less even with more storm events. 12–40% of Earth's surface will develop a novel climate, and this will not benefit food production. So the overall picture is that we have a decrease in yield, which even stresses the situation a little bit more. Look to land use and biodiversity. This is one, I would say, of the a little bit overlooked aspects in media. There was a nice article in the Standard, I think just 1 or 2 days ago, that the extinction, the loss of biodiversity is absolutely traumatic. Yeah, we are losing on a never ever seen speed, beside the great extinctions in Earth history, a loss of amphibians, mammals, birds, reptiles, fishes, and this happens today globally, and it happens in Austria. So this is, I would say, it doesn't get the attention in the media which it needs, because it's really critical. And of course, land use changes. Agriculture is one of the major players. Agriculture, as you might know, is responsible for 75% of global deforestation. And at the same time, if you have the global land surface over here, the global agricultural surface is 37%. So that's not a surprise, yeah, because 37% of the terrestrial surface is used by agriculture. And out of this, most of the land is pasture. So 70% of this 37% is pasture for cattle, for meat production. So agriculture covers an enormous 1/3 of the terrestrial surface of our planet. Agriculture expansion is most widespread form of land use change, and land use change leads to extinction, and biodiversity losses unprecedented, and species extinction rates are accelerating. So it's speeding up even. There is a nexus between water consumption, our food production, and energy, which is also very interesting. You get very different estimates depending to which data you look. There's some data here from the US, and they estimate that about 17% of the total US commercial energy use is going to crops, livestock, and then food processing, but the major part also to food distribution and preparation. Globally, the picture is even a little bit worse. The estimation is that 30% of the global energy consumption is due to food production. Let's look to water. Right now, at the moment, 70% of the water withdrawal on our planet is due to agriculture. 2050, it's expected to be roughly 90%. So aquifers are overstressed. We extract too much water from aquifer, and water scarcity will even strengthen this situation a little bit more. So 70% now, 90% by 2050. By the way, 30–50%, because that's also a lot about energy, of nitrogen fertilizers are used by plants which means the rest, 70 to 50%, is just ending up to air as laughing gas or to the groundwater as nitrate. And of course, pesticide use harms water resources and biodiversity. So from this small introduction, you can already see that food production is one of the biggest pressures on our planet. And I sum this up in this nice graph over here. And you can read this in a paper I published with a group of authors internationally from different universities in Nature Food last year. And I'm, of course, happy to share the paper if you don't have access. So the global picture is 30% greenhouse gases, 30% energy, 33% land use, 70% groundwater, deforestation 75%. And this pressure will increase with an increasing population to 10 billion. So the Sustainable Development Goals of the UN, what this lecture series is about, we will never reach these Sustainable Development Goals without fixing the broken food system. This picture here is from FAO's work on the global goals. Zero hunger, of course, is the major goal of the FAO, but there is every other goal linked to food production. Life on land, life below water, clean water, poverty, gender equality, you name it, all of these goals are linked also to food production. So we have to fix the broken food system. And I would like to cite from a very influential report in 2019. This is the Eat Lancet Commission report. I'm also happy to share this paper if you like. And then in the Lancet, Tamara Lucas and Richard Horton, they commented on this. And I'd like to read this. Civilization is in crisis. We can no longer feed our population a healthy diet while balancing planetary resources. For the first time in 200,000 years of human history, we are severely out of synchronization with the planet and nature. This crisis is accelerating, stretching Earth to its limits and threatening human and other species' sustained existence. And I think this couldn't be brought in a more precise picture. So the report is very interesting. It's for policymakers, but also researchers, for everybody, and it combines healthy diets, sustainable food systems, and the environment. So it's a corner piece for decision makers, which normally don't read these reports. I summarize basically from the World Resources Report and from the Eat Lancet Commission the few bullet points. There's of course much more. It's 30 pages, but I just summarize the few key points here. Raise productivity is the single most important step. That's not clear automatically. You could think that extensive agriculture might be the better way, but to feed 10 billion people globally, on a global perspective, they point out that a raise in productivity is the single most important step to feed the world. So link agriculture intensification with natural ecosystem protection, which is intensification, not expansion. Less emissions from fertilizers and plant protection products. So that's important. So not cutting down the forest, intensification, not expansion. That's important. Reduce, of course, greenhouse gas emissions that possible. Spur technology innovation. Manage demand, which is very important, which means reduce food loss and waste. And absolutely important, shift to healthier diets. Our diets are unhealthy. And if you look globally, in countries which are developing better and better and better, the diets go down the road and are getting worse, which means more sugars, more meat. So the key thing is here, low meat consumption, or no meat consumption, even better, but definitely we have too much meat consumption. And with this, I would like to jump to nanotechnology, and you might ask, what the heck has all this to do with nanotechnology? I'm talking about my muesli, my falafel, or my beef, if you like to, whatsoever, but not about nanotechnology. Just wait a second and I show it to you. So nanotechnology, it popped up some, let's say, 40 years ago, and I would say since 20 years it's up in the media, and some 15 years ago it gained more momentum. our group, and especially Frank Vonderkammer, who is here in the audience, and many others are working intensively in this, into also EU regulation, OECD regulation. So they're real experts here in the audience, and I can direct questions later to them also. So there are a lot of wonder materials and ideas and whatsoever. And the question, of course, is new risks, new benefits, or none of the both. That's really an important key part. So where do we have that, and what is risk, by the way? So I like this picture here from Pedro Alvarez at Rice University. What is risk? Risk is the product of hazard times exposure. What does it mean? So if you have a hazard like a shark, but you have no exposure, well, there's no risk. For example, you have a nanoparticle, which is pretty risky, but it's contained in a way that it never hits you, you never eat it or something. There's no risk. Same, of course, for the environment. Or you have exposure here to the shark, but he is not a hazard, then also you have no problem. For example, you have a nanoparticle which is benign. Let's say you have some cellulose particles or something which are harmless, and you have exposure. Also, it's not bad. So the combination here, this is the danger, that's the risk. So if you have a hazardous substance and exposure. So that's the things we have to look to. We have to look to exposure, and we have to look to hazard. And that's getting interested for agriculture, because there you want to bring nanoparticles by purpose to the field. What is a nanoparticle, by the way? I like this picture from Mike Ocella from Virginia Tech, just for you in the audience to understand the differences. If you would compare the size of our planet Earth with a light bulb, this is the same difference than a light bulb to a nanoparticle. So if our great researchers in the lab are investigating nanoparticles, it's the same thing like you would like to test a light bulb with an instrument which has the size of planet Earth. So that's the challenge here. The challenge is really huge, but we have instruments nowadays to detect particles in this size range. It's a fantastic development in the last 15 to 10 years. On the other side, nanoparticles is nothing which we invented. Nanoparticles dominate on Earth since 4.6 billion years. They have always been there. They are relevant for many geochemical processes, and they are definitely the largest reactor surface on Earth. So these numbers here, like 320 million tons per year, nanoparticles are coming from dust storms, 22 from volcanoes. They deposit on land, they deposit on the sea. And then you look to the emissions of engineered nanoparticles, that's a small fraction. And then, of course, you have incidental nanoparticles like from burning or from cities' industrial activity. So that's important also to know that nature knows nanoparticles for 4.6 billion years. They always have been there. This does not mean that engineered nanoparticles are good, but it does also not mean that by nature they are bad just because they are nano. That's just something I would like to make clear here to the audience. Where is nano used? And consumer perception is very different. There are many applications for engineered nanoparticles on consumer products, electronics, health, food, cosmetics. Very interesting to me is if you're talking about nanotech in health, like in medical applications, everybody says 2 thumbs up, that's really great. If you're talking about sunscreen, most of the sunscreens have nanoparticles. People normally don't care. If you talk about non-smelly socks, people get maybe a little bit more skeptical, but still buy socks with silver inside. If you talk about fine outdoor clothing or tennis rackets, people don't care in general. Military, of course, cares. But if we are talking about food, my guess would be people would be very allergic against this. No, we don't want nano in the food. But guys, the bad message is it's already there. You have nanoparticles inside packaging materials, for example. You have it also as additives. And now what I would like to talk today is all how people are planning to use nanotechnology on the crop in the field. And that's a big difference. You have here nanoparticles in small amounts, and this would be the first time we are using nanoparticles large scale and by purpose. So if we do this, we better have to do it right. It is not so that we know nothing about this. There is about 20 years of engineered nanoparticles, ENP risk assessment. So a lot of work has been done and a lot of knowledge has been gathered. So what I don't like, for example, is this saying, oh, we know nothing or we don't know enough. There are more than 10,000 publications, and much of this might be transferable to nano-enabled agriculture. Our group, especially Frank Vonderkammer, has been involved in a lot of projects in the EU, like NanoPhase, where people try to model emission scenarios in environmental cells in air, soil, or water, and try to estimate fate models and dynamics where, for example, here zinc adds up in which cells around London. There's a lot of work done for exposure, for risk, for hazard safe by design. So I would say we're coming out of let's say roughly 15 years globally, very intensive risk assessment of nanotechnology. So there's a lot of knowledge out there. We don't have to reinvent the wheel. And I would basically, in a nutshell, lessons learned from 20 years of risk assessments of nanotechnology in consumer products is there's a developing consensus that engineered nanoparticles pose a relatively low environmental risk. This might be surprising to you. Me as an environmental scientist, normally I'm running out there and saying, oh, risk, 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 because risk sells, risk is money. But I have to say, in general, the environmental risk is really low. And I'm a scientist, so no science without a but. Yeah. But because of uncertainty and lack of data in many areas, definitive conclusions cannot be drawn. Nothing can ever be drawn definitive. Big question is, what can be transferred to nano-enabled agriculture? Is this possible or not? There is a question on the right data. Do we really have, with tox testing here, EU or OECD tox testing, do we have the right data for One Health approach, especially like chronic low dose exposure data is missing, trophic transfer, not so good, transgeneration studies, containment of exposure will be very important for nanotech and agriculture like greenhouses or glasshouses. Another point which you can see perfectly in the pandemic we have at the moment, I like this sentence. This sentence was written long before the pandemic. Translation of incompletely understood science, incompletely understood science, that's what we see every day, into regulation and policy is challenging. I put this in very nice words, it's more than challenging. Integration of technology, innovation, and risk assessment is needed to ensure that the benefits of the technology are gained with the minimization of their possible negative effects. I would like to add a sentence here later for the discussion. There is, of course, always a risk in technology, but of course, there's also a risk in doing nothing. So doing nothing does not mean there's no risk. Doing nothing also means that because of doing nothing, there is a risk. I give you some super simple examples. Please don't read this. Don't even start to read this, okay? I just give you one simple example why it's not so easy with the nanotech and if it is safe or not is, a simple question is, can we measure what we need to see? So in this table, which you please do not read, it's just like the different regulations and provisions by the EU. And because we are the EU, we have a lot of different regulations and provisions, for example, for cosmetics. And here, a nanomaterial is something. And then we have a regulation for novel food. And this has, of course, because it's a different committee, it has to be different. And then we have a biocide regulation, which is again different. And then we have a recommendation by the EU 2011, which is again very different. So the only thing what you always see is 1 to 100 nanometer, 100 nanometer, 100 nanometer, but the rest is pretty different. There's one definition here, the overarching, which says if something is 50%, 50% or more particles between 1 or 100, then we call this a nanomaterial. And that's pretty important because just imagine for a second you have a novel food or cosmetics. Then as a producer, you need to label it, label nano, and maybe you don't want this to label nano. So here the definition is more than 50% particles in a range between 1 and 100, you have to label it nano, just to make it short. It's a little bit more complex. But these regulations are very, very diverse and very different. And a master student of us, which is very nice, a master student publishing a paper in Nature Nanotechnology, together with Frank and Antonia and Iris, which is now at Graz University. We published this paper showing that the different regulations in the EU are pretty different. So biocide regulation covers this, cosmetics defines this. We don't have to go to the details, but just to show you the definition of size, like 3 dimensions, 2 dimensions, 1 dimensions, agglomerates or materials. This is all different in different regulations. And what is maybe the same, you need to measure nanoparticles from 1 nanometer on. 1 nanometer. Your hair is 60 micrometer. Micro, that's 1,000 times more. So you have to measure something which is 60,000 times smaller than a single hair, and that's challenging. Let me guide you through this little complex figure over here. What do you have here at the bottom? At the bottom, you have the particle diameter. I just talked with you about these particle diameters, and by EU definition here, 100 nanometer, that's the definition for nano. And then the black line here, this is the percentage of the total particles, which you measure. Here, maximum is here. And then here on this y-axis, it's the cumulative particle number. So 100% of particles. And now, of course, we look for the 50% particles. So we go up the curve and see, whoops, at this point here, we have 50% of the particles measured. And this point here is below 100. So yes, this is a nanomaterial. Perfect. You have to label it and you have to register it under REACH as a nanomaterial, with different testing procedures. That's theory. Now let's go to our lab at University of Vienna or any other lab and measure the same substances in food or in cosmetics. And now just assume realistically that particles are invisible below 30 nanometer threshold. And that's realistic. If we go to a single particle ICP-MS, you don't need to know exactly what this is, and we cannot measure particles below 30 nanometers, we are blind. But this means the whole thing here, all particles here, we are completely blind. We cannot see them, which means we start there with 0%. So the first particle we measure is here, 31 nanometers. We sum the particles up. We can now realistically measure in the lab. Oops, we end up here. Whoa, 50% is larger than 100 nanometers. So that's not a nanomaterial. No regulation for this. I don't need to register it. So point is, even if we would love to do so, we cannot enforce EU legislation without appropriate analytics. And what is a law about if you cannot enforce it? We can have the same discussion with Corona. If you cannot enforce a legislation or law, a provision, well, then it's more or less meaningless. But this technique to measure nanoparticles, it's not really available at the present to go down to 1 nanometer. And this is it is a major problem for registration under REACH in 2020. Okay, and with this, I would like to go to nanotechnology in food and like to show you what will be maybe on your plate in the next 10 years. I go back to one of the first slides, plant agriculture needs help, and I add one sentence here. Nano-enabled plant agriculture is, of course, not the one single solutions. But what researchers think is, and what I would like to show you, that it has great potential and might add to other technologies. And I would like to show you today what is on the bench of the researchers globally. What are the people working in right now? Okay, so what is the idea? The topic of nano-enabled plant agriculture emerged about 15 to 20 years ago, much in the gray literature like reports, soil association, nanoscale on food. It is often said that it has a potential to revolutionize agriculture. That's claimed. I don't believe that this is true. And there are a lot of controversial discussions on risk linked to nano-enabled agriculture. So what people want to do, I show this in more detail on the slide. So like plant breeding, genetic modification, or producing nanoparticles from plants, water purification, soil improvement, nanosensors. I will show this in more detail in a second. And crop protection, of course, pesticides and fertilizers. I go to the details. What is the idea of all this? Let me guide you through this slide. So the idea starts often here. You have a nanoparticle. That's your rocket, okay? This thing is your carrier, your nanoparticle size, 1 nanometer to 100 nanometers, let's say maybe 10 or 15 nanometers. So you have your capsule, your carrier. Yeah? And this capsule could be mesoporous silica, it could be a carbon nanotube, it could be gold, maybe a little bit too expensive, or quantum dot or magnetic nanoparticle. But they also use this. I can show you why they use this. This is step number A, so you have a carrier. And then the second step is you load the carrier with a cargo. So the cargo could be, for example, a pesticide. You don't just spray the pesticide on the plant. Yeah? You put the pesticide inside the carrier and you want to release it precisely when it's needed and where it's needed. So the idea is to use less pesticide, release on demand. Or it could be a fertilizer, but it also could be DNA, or it could be protein, or it could be an activator. And then with this carrier and the cargo, you go to the plant and you release the fertilizer or you release the pesticide at need, which means maybe we don't throw 50% fertilizers to the groundwater. Maybe we can use 70% of the fertilizer. This would be a huge environmental benefit. Or we use less pesticides, less herbicides. Or you can target specific delivery of DNA in genetic modified food to, for example, the plasmons. Or you can do some labeling imaging. Is this only theory? No, it works. There's a paper from MIT, for example, Strano group, Nature Nanotechnology. They loaded carbon nanotubes, one of these wonder materials, the carbon nanotubes. They labeled it with different stuff, but they also labeled it later with mRNA. 2 years ago, nobody would know what this is. And you can see that this ends up in the chloroplast, for example. So it is possible to use such a carbon nanotube, label it with DNA, and bring this inside the cell. So the principle works, which is, well, frightening or good, however you feel about it. Another thing is, for example, nanoplant protection products. So plant protection products like pesticides, for example. It could be microemulsions or nanoemulsions. It could be smart release, that your pesticide is exactly released when you need it, or it could be metals. Future theory, no, it's on the field already. For example, here, Cupro, it's a fungicide, bactericide with copper. The same here, DuPont coicide. These are materials which are used in agriculture, and believe it or not, especially in organic farming. So if you go to vineyards, in vineyards, a certain form of mildew, it's a problem, and there this copper is used heavily as organic pesticide, but also non-organic pesticides like from wife crop production, Canada, azistarate FC, it's used, or others. So the first things come on the market now. So it is now the time where these things go to commercialization. Nano fertilizers, it's very important. I run you through this wheel of the planetary boundaries. You probably have seen this, like climate change and so on and so on. Here's the role of agriculture. So it's a little bit different picture of planetary boundaries. And you see that nitrogen, it's one of the major planetary boundaries which we stress too much. And this is, of course, mainly due to agriculture, to nitrogen fertilization. And you know these for death zones in the ocean and eutrophication. Same for phosphorus is a big problem globally. We don't have enough phosphorus. We are limited. And same, of course, for biodiversity loss. So agriculture plays a big role, and fertilizers are in this field. So if it would be able to produce better fertilizers, this would be a big step forward to a better environment. And you have some of this on the market, but to be very honest, this is only for home gardening. This is not so much used at the moment at large-scale agriculture. Very interesting. Most people are a little bit less adverse to this is nanosensors and chips. I don't go to the details here, but you can have sensors for the plant status. It's too dry, it's too hot. What is my status as a plant? And the idea is that the farmer just goes with his mobile phone, drives by the field, and the plant sends a signal to his mobile phone, I need more water, or I need a pesticide. How does it work? You have an analyte, could be water or pest or something. You can have a receptor like enzymes, antibodies, bacteria, and so on. You have the nanoparticles, yeah, and then you have a transducer. It could be optical or electrochemical, and you have a signal. And it already works in the lab. So, for example, at Michigan State University, they developed a nanosensor for pathogens. Yeah, pathogens like E. coli could be a big problem, and you can have nanosensors here which can detect easily if a batch has E. coli. Listeria, you might know, it's a big problem in systems. We also had a Listeria outbreak in Austria, I think some 3-4 years ago. And there are techniques with nanoparticles where you can have a little tiny flow cell where you have an antibody attached to a magnetic nanoparticle, get a signal, and can detect Listeria. Or same thing, you can detect plant diseases in the field with nanoparticles. The idea is you have a sentinel plant, yeah, so one plant as an indicator plant, or 2 or 3, and this plant has a nanochip, and the nanochip communicates with a reader, but nowadays you can also do this by mobile phone. So this is nothing for stuff you eat, it is a sensor in the field or for food security, basically, in the supermarket. In the paper I showed you earlier, we tried to summarize where are we, and this is one of the last slides in the talk. So we tried to summarize where are we, what is the future. It's not what we're doing in our lab, it's a review paper what is done globally. This things here is what is probably hot on the market, nanopesticides. You see technology readiness, yeah, it is already at validation, commercialization, or at field trials. So nanopesticides are getting on the market, or nanoactive ingredients. Also nano macronutrients. This is also something which is on the market. A little bit more greenhouse trial is nanocarrier bound RNA. Even more proof of concept is nanocarrier gene editing. This has a very high potential. Here we plotted the technology performance level, game changing. This has a very high potential. I would say not in Europe, but be aware that we are talking here globally in the US, South Americas, and in Asia. Why? If you do nanocarrier bound gene editing, you are editing the plant, yeah, but it's not transgenerational. And in the US and South America or Central America and Asia, this is not considered genetically modified food. So it would be on the shelf still as non-genetic modified food. And this is, of course, a big market thing. In Europe, that's different. In Europe, every step where you change something in the gene is genetically modified food. So in Europe, this will still be genetically modified food, probably not on the shelf in Austria, but in the US and the Americas, that's different. So this is very, let it call it neutrally interesting. Yeah, but what I would like to make you aware of, there's something coming which you will probably see in the next 10, 15 years up on the market and the discussions. So I would like to sum up this with probably the last slide, if I'm right. So what is the applications? Applications is, for example, these nanosensors. I would say that's probably a smart idea. Nanopesticides, if you have benign or harmless nanoparticles, that might also be a very smart idea. Same with nanofertilizers. These things could help the environment a lot. Genetic engineering, I'm very skeptical, but believe me, that's something which is on the horizon. This will come. So we need to have a careful look. Soil conditioning, I'm personally view is not big potential. So microbiome manipulation, I would say very risky. Nanofertilizers could be interesting. Seed coating is already done. Healthy seeds, yeah. Healthy seeds is one of the biggest issues, that your seeds are healthy and germ. So that's really important. So seed coating is done. What does it need? What is important? What are barriers? You need precision spraying. Yeah, nano is expensive. Yeah, so you need precision spraying and probably high value field. Aerosol mediated application is probably not what you want. You need target delivery to the roots. Yeah, you don't want to lose it to the soils. One step could be like leaf dipping or seedlings, because that's pretty precise. What's also needed much, it's material selection. the material must be non-toxic. That's key. If the material is toxic, forget it. Must be non-toxic. So best the nanocarrier is a plant-based material. Controlled exposure, like greenhouse trials, and advanced analytical tools. I told you we don't have the analyticals, and we need Sentinel sites in the next 15 to 20 years. And of course, we need a full discussion with producers, with regulators, with the consumers. And that's a discussion we need basically globally, because things which work in Austria or Europe might be completely wrong for farmers in the South Zone or South Africa or the US. So it is different in every field. Also, what we need to check the risk associated with nano-enabled agriculture very carefully. The consumer perspective is equally important as well as global perspective. We have to look at impacts of nutritional quality. How good is the nutrient? How good is the food later? We have to look to transgenerational problems. We have to look to trophic transfer, of course. We have to look to chronic low-dose exposure. This data is not available. We have to look to effects on the rhizosphere biota and symbionts, and we have to look to co-contaminant transport. And that's a nice paper from Jason White from the Agricultural Station close to Boston. So my very last slide is this one before I would like to open the discussion. Innovation and precaution are important. Yeah, some people are more on the innovation side. That's also interesting in which country you are. So both is important. Innovation, we need innovation to feed this planet. That's no question. I don't say that it's nano, but nano has potential. But precaution is also very important. So in the case of agriculture, covering 1/3 of Earth's terrestrial surface, you better do it right. This would be my last comment. Thank you very much for listening.